Good morning, and welcome to the Black Mesa Transit System. Now arriving at Sector C Test Labs and Control Facilities. Thank you, and have a very safe and productive day.
Oh hey, it's me, Science Man. So I went a little crazy over the last 6 months, and I turned Blender into a working version of Half-Life. I built it in my homemade game engine that I developed inside Blender, and you might have some questions, but don't you worry, I have answers. So I'm sure you already know Half-Life, massively influential, one of the best games ever made, blah blah, you know how it is. It holds a special place in my heart, and it really is an all-around fantastic game that's still worth playing close to 30 years later. When I was looking for a project to take on with my game engine, Half-Life came to mind right away. Although I didn't recreate anywhere near the entire game, I did my best to recreate a lot of the original systems, and all the functionality is built entirely from scratch, but I did use the original models and textures because I'm a little bit lazy. Because there's so much going on here that I'm excited to tell you about, I couldn't fit it into a single video, so I'll have to break it into 3 separate episodes, and in this first episode, we'll look at the Black Mesa Employee of the Year, Dr. Gordon Freeman.
Hello, Gordon Freeman. It's good to see you.
We'll look at how his movement systems work, included creeping through vents, dying in an elevator shaft, flying off into the upper atmosphere, and so much more. I'll compare the original game to my knockoff version, and then break down how I went about implementing it into Blender. So let's get the big question out of the way first. You're probably wondering, why even go through all this effort? Honestly, my big reason is that I just really enjoy projects with interesting problems that are fun to work on, and recreating my own version of a game definitely falls into that category. As a bonus, it's also a very good learning opportunity for expanding the capabilities of my game engine. Even though the actual implementation is unique to Blender and requires some outside-of-the-box thinking, the core principles are universal to games as a whole, so the math, design, and concepts are transferable to game development pretty much universally. This whole project is built with geometry nodes, which is Blender's system that allows you to make procedural mesh setups. You don't need to be familiar with them for this video, and for the sake of time, I'll just leave it at that. If you're interested, you can check out some of my other content. My game engine, which I call BlendWorks, already has a series going on my channel with some more in-depth breakdowns, and I'll leave a playlist to those videos in the description if that sounds like something you'd be interested in. Now, just a note, because of those other videos, I won't cover the basics of the movement system, but you don't really need to know about those things for this video anyway. So games are built out of systems. They range in complexity from really simple to super duper complex. These systems are usually interconnected and dependent on each other, and because of this interconnected nature, nodes are a pretty good way to visualize them, because you can see directly how things are connected in a pretty literal way. We'll dive into a bunch of these systems that I built for the Half-Life recreation very soon, but I think it'll be helpful to look at 3 major building blocks first: simulation zones, vectors, and booleans. So here's a map of the project, composed of hundreds and hundreds of individual nodes. Most of these nodes are encased in a maroon box, which is the simulation zone. The color of the lines connecting the nodes represents the type of data being passed from one node to the next. Green is all the geometry, handling the visual, real parts of the game. Purple represents vectors, and pink represents booleans. So this is a lot to look at, but let's simplify and illustrate with a simpler model. Let's say Gordon is out enjoying a pleasant walk. As far as game function goes, simulation zones, vectors, and booleans are all at work here. Let's start with a look at the simulation zone. Games are all about change and the interesting way that change happens. Change, by definition, needs time. Transforming something into something else has at least 2 distinct points in time. So games interact with time in one way or another. For my game engine, the Blender simulation zone is the secret sauce. A sim zone is just this box that allows us to use the state of a value from the previous frame to influence the output for the next frame, which means that we can change values over time. Let's take a look at a really simple example. Here's a very basic project that has a transform geometry node that allows you to move Gordon on specific axes. The problem here is that the value defines Gordon's overall position, not the way it's changing. But if we add this simulation zone around the transform geometry node, we've just made a system that can change over time. We can throw all sorts of stuff in the simulation zone to process that change however we need. To actually use this system, we'll need a way to define where Gordon is, where he's going, and how fast he's going there. And that's where vectors come in. Since most games are all about movement, vectors end up being kind of useful. Vectors are just a set of numbers that define direction and magnitude. In 3D space, vectors have 3 components, one for each axis. While Gordon is walking, he actually gets 2 different vectors because he's a special guy. One of his vectors defines his position, or where he is in the world, and his other vector defines where he's moving, or his direction. The scale of this direction vector defines how fast he's moving. Now, I gotta be honest, I freaking love vectors, which is weird because I was scared of them for years until I started working on this whole game engine thing. They're just such a beautiful way to define change in space. One really cool thing about vectors is how we can transform them pretty much however we want with math. We can move them, scale them, and rotate them, all in 3D space. Now, the player does have some direct control over these vectors. For example, by moving the camera, the vector rotates and changes the vector's direction. There are a lot of limits to the amount of control though. In real life, physics has a lot to say over what you can and can't do. Like you can't just walk through a wall, for example. As Gordon walks, he eventually reaches an obstacle, so what's to stop him from walking through it? And this is where Booleans are handy. Alright, one more overgeneralization. When you boil down the technical side of any game, it's about controlling the ways players can interact with the world around them while keeping things fun and interesting. Games have rules, and game development is all about enforcing those rules. Boolean true and false, along with switches and logic, have really simple building blocks that can be combined into some seriously cool stuff. The device you're watching this video on right now is a great example. Computer chips use simple logic gates that are combined by the billions to process information. So anyways, based on the data from the game world, such as those vectors we just covered, Boolean logic can allow or prevent things from happening via switches. To illustrate how this works, here's a sim zone loop, and there's variations of these sprinkled everywhere in this project. For this example, if the condition is triggered and changes from false to true for even a single frame, it locks and then stays true until the timer releases the lock after a set time of, in this case, 1 second. This system works because the sim zone allows the Boolean of the previous frame to be evaluated against the current frame. The condition for triggering or releasing a switch can be whatever we want it to be. And we'll see plenty of examples of how useful this logic loop is. Alrighty, enough with theoretical examples, let's take a look at some real stuff from the game. We'll start with jumping, which is a great example of a system that uses vectors, logic systems, and simulation zones. The actual movement of a jump is just an upward pointing vector. When the player jumps, this upward vector gets added to the existing player movement vector by a switch, combining the 2 vectors into one. Jumping happens when the input script detects the spacebar being pressed, telling the node system to add this vector. So that's great and all, but there's a big problem. Unless we limit how long a jump can last, then a player will just fly off into space as long as they hold the spacebar. To build a limiter, we'll need a way to measure time, starting when the player leaves the ground, which is measured by a raycast. A raycast is basically just a way to measure the distance from a point to a mesh. A logic system passes through the player input until a time limit is reached. So the jump output is true when you hold the spacebar, and false when you stop holding the spacebar, until the time limit is reached, and then the output is false, even if you hold the spacebar until you contact the ground again, and then the timer resets. Managing edge cases is important, and a lot of the time it's basically impossible to eliminate all of them, but there are some big ones. With jumping, one of the more obvious is the potential to jump into a ceiling. This works in a pretty similar way to regular collision, where there's a check to measure that the player isn't too close to a ceiling. A raycast points upward and measures the distance to a mesh above the player, disabling the jump if the distance is too small. While we're on the subject of jumping, let's talk about fall damage. Just like a lot of other games, Half-Life has fall damage, so I added it to my version as well. There are different ways to go about this, but I went with a pretty simple system that measures how long a player is falling downward, increasing the velocity over time. If a certain velocity threshold is reached, damage starts to accumulate, but isn't actually applied until contact with the floor is made. There's a sim zone that tracks the player health that takes inputs from anything that can potentially impact the health pool. Fall damage acts like a sort of cache, where the fall velocity system tracks the damage that needs to be applied, and once it's time to apply the damage, it gets transferred to the player's health system in a single frame. To keep Gordon from being too fragile, there's a minimum fall damage threshold to keep a small amount of damage from applying when Gordon just does a normal jump. Crouching is functionally the opposite of jumping, moving the player down instead of up. When crouching, a couple things happen. The player's distance from the ground decreases, which moves everything associated with the player down as well. Things like the camera and the player position. The crouch itself is animated, since completing the entire crouch distance over a single frame is a bit too jarring. I used a modular animation system that moves a certain amount per frame up to a maximum. It uses the same principles as the jump limiter system, but instead of outputting a boolean true or false, it spits out a number. Now the cool thing about that number is that it can be plugged into one or multiple axes for position, rotation, or scale, allowing any one of those to be animated. Because of the modularity, they can then be strung together or combined to create more types of animations. This is used all over the place, but specifically for crouching, it's applied to the player's Z position, and these systems also have a simple calculation to factor in frame rate, otherwise everything would run slower at lower FPS and faster at higher FPS. Because this project uses geometry nodes wherever possible, all the animation is handled this way instead of using a more traditional keyframed animation, which honestly would have been a lot easier. Geometry nodes aren't designed for keyframed animation, and because most animation needs to happen dynamically, this just isn't an option currently. I'm sure there's a way to use Python scripting to add keyframes to the timeline, but for now, because of the way I wanted to design this project, everything is animated with number values. So just like jumping, ceilings are an edge case that can potentially break the game. The crouch system is constantly measuring distance to the ceiling using that same upward raycast as the jump. So if the player enters a vent or other tight space where the ceiling is lower than the normal standing height, the game overrules the user's crouching input, which entirely prevents them from standing. Once the raycast measures more vertical clearance, then the user is allowed control again. So now it's time for a message from our sponsor. This episode was sponsored by me. Would you like to get your hands on the blend file for this project? If you like what you're seeing, are curious to try it out for yourself, or just want to support the channel, then you can check out my Patreon. I put my video Blender files up there, so you can go check it out. Just as a note, I didn't want to put anything up there that I didn't make myself, so I took out all the Half-Life specific stuff and just made a version with all the systems that I had built in a more generic environment, which you can think of as like a playground of all the features that I built. Anyway, go check it out if you want to. Add over. One of the first things you'll notice about the movement in Half-Life is the loose, slidey feel. The camera tilts as you walk, and there's a bit of sliding after you stop moving, almost like you're walking on ice, where the movement just keeps going for a bit. It is subtle, but it just doesn't feel right if there's not a touch of it, and it does a nice job of giving you a sense of weight. To replicate this in my version, I used the animation system applied to the camera's rotation along a single axis. If you press the W key to move forward, the animation node group will rotate the camera's local x-axis positively, which makes the camera look like it's moving backwards, which conveys a nice sense of inertia. This applies to the other movement directions as well, of course, and the camera will rotate away from the input direction. To recreate Half-Life's slidey feel, I built a node group that decays movement over time. I designed the game system with an input processor that combines all the user inputs into a vector. But before this vector is processed, I added an input slide node group. This group passes the value through normally each frame until the input is 0, which means that the player has stopped moving. At that point, the previous movement value is passed through instead, after it's multiplied by a scalar of less than 1 each frame until it eventually just becomes effectively 0. This can be adjusted to make it feel just right, and the closer a value is to 1, the slower the decay will happen. As you can see here, a value of 0.99 is probably a little bit too much. You just go flying off. For that half-life feel though, I felt a value of 0.92 felt about right. One standard FPS feature that I don't really think about very much, but I definitely notice missing, is a look limiter. The camera should be able to look around from side to side as much as we want, but if there isn't a maximum or minimum on the up or down, things can become pretty disorienting when the camera rotates to face behind the player and then everything is backwards. It seems like a pretty simple thing to build, but ended up being kind of a complicated situation, and I think the final solution ended up having some pretty interesting stuff going on. So at first I just tried setting a maximum or minimum value on the look rotation with a math node. This did work to prevent looking up or down past a set limit, but because the mouse position directly controlled the input, if you look too far past the limit, then try to look back, it would just stay stuck. Giving the total rotation its own separate value prevents this, but there still needs to be a way to quantify how much the mouse is trying to move and add that per frame. So one of the cool things you can do with simulation zones is calculate the difference between values. To do this is pretty simple. You just plug the value into the output of the sim zone and then pull it again from the input, which stores the previous frame's value. You can then just subtract the previous value from the original input value, which will give you a number that represents how the value has changed in the last frame. Using this to drive the camera and process the input every frame works great, and disabling anything from being added if the final rotation is beyond a limit does the trick for limiting up and down on the camera. The last thing we'll cover today is the interface. It's pretty simple, basically just a tiny scaled text that's placed right in front of the camera to avoid clipping through surfaces. I mean, if it's too big, something like this happens. The UI needs to follow the camera as it moves and rotates around the world, so all of those vectors are passed through from the input processor to the interface system. All of the relevant values that are needed to display in the interface, like the health and ammo, are plugged into this group as well, giving the player all the information that they need. Part of the interface is the flashlight, which works the same as the regular interface. It just places a spotlight on the player's position. There's also some extra Python code handling toggling on and off, and a switch changes between two versions of the flashlight icon depending on the status. So anyway, there's a look at some of my Half-Life remake. I hope it's been an illuminating episode, but there's still so many things I want to talk about. I think Gordon's on the loose, so I gotta get going, but I'll see you in the next episode. Thanks for watching. Appreciate it.